I don't remember. I don't remember.
90?
I mean, I graded it like a week ago.
20?
Huh?
I was asking if the average was 20.
If it was 20? Well, I don't know. It probably wasn't far off. I know most people didn't like do well. There were a few students that did really well. But, yeah, for problem 2, the way some people parameterize everything, like the whole exam. I wouldn't necessarily recommend that, but if you want to do it, it's fine. So for problem 2, if I were doing, there were 2 surfaces that I would not parameterize. And to actually compute those, I gave you 5 points each. And the surface that I would parameterize is the vertical part itself, the cylinder, and I gave you 8 points to evaluate that. And then I gave you 2 points for knowing that you had to add all the answers together.
Question. For our following exams, we'll continue to have bonus questions, right?
For what?
For our next exams, we'll continue to have bonus questions.
All exams have bonus questions.
Okay. And will they all be something we didn't learn, or?
That's in general, yeah, that's it. Yeah.
For the progress is towards where it says rank, that's a rank, like according to our grade?
Yeah, that's a grade to the rest of the class. In problem 3, if you got up to finding the n and the magnitude of n, I gave you 10 points for that. To set up the integral, I gave you another 5 points, and to just evaluate the integral, I gave you 5 points. In problem 4, I gave you 5 points each for the setup. And then in part B, I gave you 10 points to evaluate the integral. Which is weird. A lot of people skipped problem 4. Like skipped it, completely blank, didn't write anything. It's Calc 3. I actually just set up a triple integral and evaluate it. I described it, even say set up a triple integral, evaluate it.
Maybe they didn't have that page. Maybe they didn't have that page.
I don't know. In problem 5, there were again 3 curves. I gave you 6 points each for doing the integral along each curve, and 2 points for adding the answers together. Right, so for the bonus point, I think I gave you 2 points just for writing the formula down, 6 points to set up the integral, and 2 points to evaluate it.
Question. So if we got 90 in this exam and we get 90 in the next exam, then we'll pretty much use 5 per exam.
Come again?
So if we get 90 in this exam and get 90 on the next exam, then we're pretty much set, pretty much, in terms of our exam grade.
Sure, yeah, the best 3. I think the best 3.
Best 3, okay. If we get up to 3.
Of course, if you decide to take the lazy way out and you get 95% on the first 3 exams and decide to skip the 4th one, I just might average yours out of 4.
Are you fine handing out the exam?
I was. You have to pick it up at the end of the class. So some other comments, not ranting comments, but general observations. Line segments have orientation built in. I noticed that there were some people that you were parameterizing line segments, and when you're doing the integral, you decide to put a negative sign because I said it was going clockwise or something. You don't have to change sign or anything for lines. The orientation is built in. The formula has initial and final in it. The line itself knows what direction it's going in. Orientation is a part of the formula. So you don't have to change orientation for a line. Write that down. Comments on parameterizing line segments. At least when you're using the formula I gave you. If you parameterize on your own, then all bets are off. Right? There are many ways to parameterize a line segment, but if you use the formula I gave you, orientation is built in. You don't have to change it.
Okay.
So you don't have to negate the integral, you don't have to switch the limits, you don't have to do anything. Orientation is already a part of the formula.
Okay.
Yeah, I wrote here, people don't know where the 4th quadrant is. Okay. Right, so the difference between using polar coordinates and parameterizing is also something. When doing a surface integral, need a Jacobian. Everyone knows what the Jacobian is.
Jacobian is the determinant of the partial derivatives with respect to each of the
That is true.
variables.
Most people didn't read that chapter though, so let me explain. Like if you're doing polar, right? You're writing dA, it would be r dr d theta, right? This r here, this formula here that you have to put in front of the d's, that's called the Jacobian. That you get it from the derivative, the determinant of the partial, blah blah blah. But you didn't really talk that. Or if I'm doing dv in like spherical,
It's a rho squared sine phi.
then it would be rho squared sine phi d rho d phi d theta, right?
Is it really how-
This guy here is called the Jacobian.
Is
Now if you do a problem where you're parametrizing, where you say you parameterize x equals r cosine theta, and y equals r sine theta, right? When you go through and you set up the integral, you do not put the r, you just put dr d theta, right? No r. Okay? How do you know when to use polar or when to use this guy? It's when we use Jacobians if we
Integrate?
set up the integral without a parameterization. In r theta or rho p theta, but later convert the integral to compute. Right? So you set it up, there are no r's and thetas, and then you decide to switch to polar coordinates in order to evaluate that integral. Then you have to do just like you did regular polar coordinates. But if in the beginning you're defining your vector function using polar coordinates as an inspiration for your parameterization, then you don't put the Jacobian. It's just straight up dr d theta or d rho d phi d theta.
Alright, I just had a question about the Jacobian. So the Jacobian is the determinant of the Jacobian matrix, right?
Yes.
So like back in the class you said you couldn't have a gradient of like a vector, but you think of the Jacobian matrix as like kind of like a dyadic product of the del operator and the vector. Like is it possible to think of it like that? The actual matrix, not the determinant. Like if you think of the matrix, it's kind of like that.
Right. It would still fall in line with the
Yeah, but could it be like,
the operations. Yes.
is it kind of like analogous? Is there any analogy between like,
It's sort of, but you really have to talk about, the whole point of Jacobian is to do the whole change of variable thing, so I have to talk about translating spaces. I'll talk about it, we can talk about it later. I don't want to get into it right now. Yeah, so I said a lot of people here just parameterized everything, and they ended up making a mistake because of it, because it's a lot more work. And a lot of people also ignored the radius, so I would give you like a circular radius 3, you know, I would say like x squared plus y squared equals 9, and I don't know, z equals, z goes from 0 to 5, and a lot of people would say r u v is cosine u, sine u, right? Like, they forgot the r. Right? So be careful of that. This, like, a lot of people did that. I don't know why. Like, they just ignored the radius. Let's see. Yeah, one other thing, how you draw your axes. According to the textbook and the convention that I use is that I let z go up top, x goes to the left, y goes to the right. In general, there's nothing wrong with writing this in another way, but you should know that when we describe a region in words, like I say, something is to the right of the XZ plane, and to the, or when you're looking from above. This is the picture I'm thinking about when I make those descriptions, right? So when I say looking from above, I'm thinking of you're looking down in this direction, right? So if you draw it like something like X here, Y here, and Z here, that's fine, but you should know that above would mean looking in this direction, right? So you should be careful, right? It's just a convention, but when I describe a region, this is the convention I'm using. So be careful of that. So a lot of people were drawing their axes in a different way, and because of that, they sort of looked at the region differently from how I wanted them to look at it. Yes?
I get confused sometimes when we use R, just general R cosine theta and the actual radius cosine theta or whatever.
Oh, it comes when you actually want to, if you're doing a circle, it has to be a constant. Right, basically you would use, if you have like a shaded disk, right? So from the center, you want everything from the center going outwards. Then your R has to take on a range, right? Your radius has to go from 0 when you're at the center to the outside radius, right? But if you just want the circle, just the edges, then R is equal to some constant.
In which case,
right? So for example, a cylinder, I would just let R equals a constant. I wouldn't write R, I'd write the actual constant radius. Well, if I was doing a solid cylinder in 3 dimensions, then I would have to leave it as an R and let R range from 0 to the radius. So it depends on if you want this thing filled in or not. Right? So for this, you leave R as a variable and just let it follow a range.
And when we're like finding, say, I don't know, like the area of a cone, R is constantly changing, so it has to be R?
Yeah, if you're integrating over a cone, that's going to be an example, right? Because based on the level you're at, the R is changing.
Yeah.
Let's see. Okay, when switching orientation, right? So let's say you're in a situation where you have to switch the orientation.
do we have to ever?
Yeah, there are times. Like if I say you're going
Counterclockwise?
clockwise around a circle or something like that.
No, we can do
You
it.
can, on an integral, you can negate the integral,
But don't double negate it.
or switch the limits on the integral.
That's the exact same thing.
Not both.
Didn't you say this last time, in last test?
I did. Yeah, I'm just going to say it again. All right, so it's like you turned around and then you turn around again. You did the limits. You changed the orientation twice. So for example, if I say at x squared plus y squared equals 1 clockwise, then you know that right, so you have this circle here, and I'm going around this direction. And then you could either, when you're setting up the integral, blah, 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 dt, you can either put a negative sign here and do the regular 0 to 2 pi if your r is equal to cosine t sine t, right? Or you could just go from 2 pi to 0, right? Da, 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 dt. If you did the negative of 2 pi to 0, that's wrong. Because what you did, you put the negative, that switches the orientation, but then when you switch the limit, you switch it again. You go back to where you were in the beginning. Yes?
The Jacobian thing doesn't apply to regular line integrals?
The only places you encounter Jacobian is if you're doing like polar or spherical. You don't really have to worry about it in other situations.
So,
But the idea is, if you use these guys, these coordinate systems as your inspiration to parameterize in the first place, then you don't need the Jacobian. It's if you set it up without these guys, and then you have this integral that you choose to evaluate it using one of these guys, then you have to put them, right? So you don't always put them.
Because even if your region is like you're doing over D and B is a circle too, you don't use the Jacobian either? Like after you parameterize?
It's only about parameterizing. If you parameterize with polar coordinates or spherical coordinates, like it's a part of your parameterization, you don't put it.
so basically in that case right there.
Right. Is if you set up the integral without doing that, and then you want to change the integral so that it's easier for you to work it out, then you do it. right? You're back in Calc 3 right there.
So it just depends whether you're going to get or not.
Yeah. Another common mistake, and here, literally from 0 to 1 and t dt. That's actually a half. More than half of you think it's 1. Right? Integrate this, it's t squared over 2. Right? And you get a half.
How much did they lose?
That's really generous. I probably took off like 1 or 2 points or
Okay.
something like that, which I think is generous. Yeah. Other than that, I guess we can begin.
So today we can finish Divergence Theorem.
Yes, finally. So don't ask me any more questions and slow me down. You guys slowed me down last time with all your Stokes theorem questions.
So the class is finally over.
So let's finish up. We're going to continue with the divergence theorem. One last example,
Okay, nice.
and then we move on to linear algebra.
So calculus is done after that.
A nice change of pace. We're going back to the easy mathematics where we just have to worry about just adding 2 numbers, multiplying 2 numbers, subtracting 2 numbers, stuff like that.
Why did they wait till the end to get us to this?
We won't have to know where the quadrants are, so we should be okay for the most amount. So very little pre-calc is in here, so you guys should do better. 13.9 continues.
So bright side calculus will be over.
Yeah, this is the last thing in vector calculus. Missing it already. Remember, another name for this integral is the flux, right? So instead of writing that integral down, I could have just said compute the flux. Right? You guys should know what that is. For S. S. Is so we had a certain, and I have to tell you what the vector field is. X squared plus sine z, xy plus cosine z. Today is 4/15th, tax day.
Oh yeah, yeah.
Is Rommel here? No. This is up there, I saw him. Frangio? Walter? Sally? get to it. So we had a problem similar to this on the exam, actually. So in theory, you know how to do it the long way. This guy's going to be a cylinder here. This would be z equals 6 minus x, which means it's going to slant like this way. So it's going to look something like this.
Sure.
What's the quick way that you know that it's going to slant that way? What's your thought process on that?
I thought of z equals 6 minus x, which means if I'm drawing z versus x, the line would go down this way. So I know it's going to touch the positive z-axis, and it would hit eventually the positive x-axis. So that's just
So why isn't the bottom slanted as well?
Huh?
Why isn't the bottom slanted as well?
It's the xy plane.
Oh, okay.
So it's a
you're
flat, it's
stopping
on the
there.
floor.
Okay.
So my thing looks like, the surface looks like that. It's very similar to the guy on the homework. So if we're doing this the long way, we'd have to do a surface integral here, plus a surface integral on the cylinder, plus a surface integral on the flat plane. I wouldn't parameterize with these two. I would just use, you could use n, with positive orientation, just use minus fx, minus fy, positive 1. Here I would use n equals fx, fy, negative 1, which ends up with be 0, 0, 1, negative 1. All right, and then here I parameterize, right? I use r of uv equals, the radius is 2 cosine u, 2 sine u, and then v. And so I was thinking polar coordinates when I set this up, but it's actually, I parameterize in polar coordinates, so actually when I get to the integral part, I'm not going to have an r. I'm not going to have the Jacobian, right? Because I actually use this in the parameterization.
Yeah, but not in terms of v, theta, and r, just u and v. Right?
Yeah,
So.
it's just in terms of u and v. Right. So, especially students get mixed up when they use the old notation in their parameterization. So some people might leave this as a theta and things like that, so then they sort of think polar coordinates when really it's not polar coordinates. It's just a parameterization.
I mean, that's how we learned it in terms of u and v.
So, that's why when you're parameterizing, I like to use u and v, so you don't get into the habit of just regurgitating all the formulas you know with r and theta. Okay. So, yeah, so that's our region. So this would be the long way to do it, and you have to do the surface integral over each surface. That's what you had to do on exam 2. But now that we have the divergence theorem at our disposal, we can actually get to it easier. The double integral over s, the flux dot ds, is going to be equal to what, according to divergence?
Triple integral of the divergence of your vector field.
Triple integral of the divergence of the vector field v. This is over e. This is by the divergence theorem. So then this would be equal to
2x plus y plus 0.
right? Let me just write that down. Divergence of f equals, so you take the partial of the first component with respect to x, partial of the second with respect to y, partial of the third with respect to z. That's going to be 2x plus x.
Yeah, sure.
That's just 3x. So this implies okay, how do we set up that triple integral?
I recommend polar.
0 to x minus.
Right. So here, this is what I'm talking about. I set up the integral. It doesn't have r and thetas in it, right? So if I do decide to switch to polar at this point, I have to put the Jacobian, right? So yeah, how would I set it up?
0 to z minus.
Well, x is going to be r cosine theta. So.
Inner integral, you're telling me?
6.
Yeah.
0 to
Theta, right?
To x minus.
6 minus cosine.
X equals r cosine r theta.
6 minus x. Right? If I solve for z, I get 6 minus x.
Yeah.
I'm doing
Which
dz.
is gonna.
We're doing dz dr d theta, right? So I have to do r dz dr d theta, and so I know my theta would go from 0 to 2 pi. R goes from what?
0 to
0 to 2, and then this goes from 0 up to 6 minus x. But
Yes.
I'm switching to polar now.
6
My
minus
x is r cosine theta, and then I have 3 r cosine theta. No, because I have limits here. I have to worry about that later. wouldn't try a trick like that with limits that aren't constant. So integrate with respect to z, I would just get a z here and then I plug this in. So I really have 3r squared cosine theta times 6 minus r cosine theta. So now I would just expand 0 to 2 pi, 0 to 2 of this would be 3 6 is 18 r squared cosine theta minus 3r cubed cosine squared theta drd theta. Remember 0 to 2 pi constant limit, so I know this is going to go to 0, so I forget about that. Cosine squared, how do we do with that guy?
Make it 1 plus cosine 2 theta over 2.
No, no,
So
1
1 plus cosine 2 theta over 2.
All multiplied by 2.
Yeah.
No, 1 plus, it's 1/2 plus.
No, I do 1 plus. I consider numerator first and then divide it by 2. Yeah.
So that's going to be your guy, but then the cosine 2 theta is going to go to 0 as well by our previous thing. So this integral really just simplifies to minus 3r cubed over 2 drd theta. So integrate with respect to r to the 4th over 4.
Where did 3 come from?
The 3 was there in the beginning, it was 3x.
Oh, I'm sorry.
D theta. So then you plug in 2 to the 4th is 16 divided by 8. Right, so I get 4, so this just gives me, that would give me 2 pi times minus 3 times 16. 3 times 16 over 8. Right, so this goes into that 2 times, and then I multiply by 2 again, so that's minus 12. Flux. So the long way you did it in the exam in test 2, so you would know how to do that. If you don't know, I have posted the solutions online, so you should know by now. And this would be the other way. So in the next test, for example, I'm going to ask you to do both ways. Right? I'm going to give you a divergence theorem problem and a Stokes theorem problem. And I'm going to actually compute the long way and then compute the short way. So the long way you should know by now, this is how the short way would look like. Right, so we don't need to set up 3 different surfaces, parameterize 1, and do 3 of these integrals. We can just do one triple integral, and it does all that work for us. Right, and that is the power of the divergence theorem. Any questions?
Would doing it the long way be a bonus question, or would that be?
No, it would be a
No, it'll be full question. Okay, so we're done.
Is that it? Any questions? So that actually does it for vector calculus. So right now, we can just
Finally
do,
finished calculus.
yeah. So right now we can do a summary.
A summary of calculus.
A summary of calculus, exactly, all of calculus. Right, we finally know everything we wanted to know about calculus. Right? At least as far as college is talking about, right? So if someone asks you, what is calculus about? Well, it's about limits. That's all calculus is, really, the study of limits, right? The derivative is a limit, the integral is a limit, and calculus is about integrals and derivatives. It's all about limits. But then you ask, what is the highest ideal of the integral and limit? What is the thing that they really give us that's really important? It's the theorems that we've covered, the summary of calculus. Right? This is the fundamental theorems. The things that when you're studying calculus, this is our goal to teach you.
And
Of course, the very first one you learned in Calc 1. This is called the fundamental theorem of calculus. Right? This was the one that opened the floodgates, really made us think about calculus in a different way. This was if you know that the integral of f prime of x dx from a to b is equal to f of b minus f of a, right? And this was when you were on an interval. You're like on the x interval from a to b, right? So that was the fundamental theorem of calculus. So everything you learn about integrals and derivatives culminated in this theorem. Right? This is just one part, but that's a very important part. Part 2, we started to generalize our notion of the integral on a curve. And we generalized this to the line integral. And that led us to the fundamental theorem for line integrals.
It feels like you told me to calculus too.
Right? So we sort of generalize this notion of, we don't want to integrate over the interval anymore. We want to integrate on some random curve. And for that, we got the fundamental theorem for line integrals, which told us that if we took the integral of f dr from from r of a up to r of b, that was just equal to f of r of b minus f of r of a. Right? That was our fundamental theorem for line integrals. Right? So that was the second important theorem in calculus that we covered, and we took all the way to 391 to actually learn about it. The third one, guy is actually Green's theorem. Here I told you that if we took the integral along C of p dx plus q dy, that we could actually write as a double integral of qx minus dy. Is that the direction I want to write it? I actually want to write it the other way. Because I'm actually going to draw a parallel, so let me write it the other way. So that was Green's theorem. Fourth was Stokes' theorem. Right? And the notion in Green's theorem is that we had a closed curve and we had a region that was bounded by the curve. Right? Notice here that we have a curve, but A and B are the boundary points. Right? So here we have, in this theorem, we have a zero-dimensional boundary points. In this theorem, we have a one-dimensional boundary point. It's basically sort of the same theorem, except we're upping the dimensions. Right? 4 was Stokes' theorem if you up the dimension a little more. And that told us which direction I want to write that in. And in this case, I had a surface, and my C was the boundary curve of the surface. Then finally we did divergence theorem. And we said that the triple integral of the divergence of f dv was actually equal to this. Right? And here we had a solid figure, right? So here we had a solid figure called E. Right? And S was actually the boundary surface. S is the boundary of E. Right? So these are the fundamental theorems of calculus. In college, when they want to teach you calculus, these are the 5 goals that we have to teach you. These are the fundamental guys that we try to get to. Right? And for the people who haven't taken vector calculus, they actually miss most of the big picture. Right? So this is the big picture. This is what calculus is about, the fundamental theorems. And you'll notice that they're all really about the same thing. We are relating the integral of a derivative to the integral over the function itself. Right? So we're here, you can think of the gradient as a kind of derivative. You're relating it to the function itself. Here you can think of this as a kind of derivative, partial derivatives. You're relating to the function itself. The curl you can think of as a derivative, you're relating to the function itself. The divergence is a sort of derivative, you're relating to the function itself. And they're all talking about a region and the boundary points, right? If you take the integral of a region over the boundary points, it's the same as the original function over the region, right? That's what all these theorems are actually saying. This is what calculus is trying to tell you. And it turns out that these theorems are a lot more powerful than any of us realize. Even me, I would say. I haven't studied it. that deeply, but that's the goal of calculus, that's the summary. And now, at the end of linear algebra in 391, we've seen them all. So we can pat ourselves on the back. I mean, we don't know where the quadrants are, but you know, I know what the fundamental theorems of calculus is, right? And those are they. So, pre-calculus is a different story. Calculus we got under control. Oh, advanced calculus, you basically go over everything you do in calculus, but you prove it rigorously. Right, so I wouldn't just tell you, oh, that's a fundamental theorem of calculus. You prove it now. Why is that fundamental?
So there's nothing new.
Why does that make sense?
So there's literally nothing new.
No, you just go deeper instead of wider. So first you go wide and try to cover a wide range of topics, then you go back and go in depth, dig deep.
Functional analysis.
Oh, that's advanced calculus. I'm talking about elementary calculus here. Elementary calculus.
Awesome, okay.
Yeah. That's the summary of elementary calculus. That's that's what engineers need to do.
That's all I
So that's it. And with that, we can start linear algebra.
So it took us 2 years to get to here.
Yep. 3 years to get.
Well, 2 years for my freshman. I think my freshman was 1 year.
So now we're actually going to begin part 2 of the course. Maybe I should call it elementary linear algebra because we're really not going to go that in depth. We're really going to study like the tip of the iceberg with this stuff. We're really going to talk about, in particular, matrices and how we can use them to solve interesting problems, specifically systems of linear equations. Later on, we're going to learn how to solve systems of differential equations, linear differential equations. If you haven't taken differential equations, don't worry about it. It's actually not that big a deal. The situation we're going to deal with is pretty easy to just teach you right on the spot. So that's what we're going to get to, but of course we're going to need to build up some vocabulary. Just in case you haven't seen linear algebra before, I'm just going to have to tell you how we speak the language of linear algebra. So we start with chapter 1, and we're going to just cover some basic definitions. It's matrices and matrix algebra. Right? How do you do algebra with these things we call matrices?
Is matrix algebra like junior high stuff? Is matrix algebra like junior high stuff?
Is that an and? Matrices and matrix?
Yeah, yeah, and. Okay, so definitions. First thing, I mentioned matrices here and matrix. Let's talk about what that is. Matrix. This is a rectangular array of numbers. A rectangular array of numbers or symbols we call a matrix. The plural is matrices. So when I say matrices, I just mean many matrices. Like the plural for matrix is matrices, right? And a matrix is a rectangular array of numbers. For example, here's a notation. 1, 2, 3, 4, right? This is a matrix. It's a rectangular array. I'm ordering numbers in a rectangular fashion, right? Or 1, 2, 3, 4, 5, 6. That is also a matrix. Some books might use the notation brackets, like this, 1, 2, 3, 4
lines.
I don't like to use them because it takes too long to write down. I have to make 1, 2, 3, 1, 2, 3, like 6 strokes instead of just 2.
Can you just do lines?
Lines you cannot do, right? So if you have something like a line, like 1, 2, 3, 4, this is actually the determinant of the matrix 1, 2, 3. right? When you do straight lines, just vertical lines, you're taking the determinant,
So you're solving.
right? Which we're going to talk about later on. There's a whole chapter on determinants.
Really?
Yeah, so.
But didn't we do determinants all calculus 3?
So that's, you did one determinant thing. You did like a cross product. That's the only one place you use determinant. So here we have, that's a matrix, right? So you order a bunch of numbers in a rectangular fashion, draw some parentheses around them, you get what's called a matrix, yes.
Do the elements have to be homogeneous or anything?
No. Right? Just any collection, any random. So that's the matrix. 2. The numbers or symbols in the matrix are called elements, or some people call them entries, or you can call them components. If matrix is a vector, which I'll define later. Matrix is a vector. It's not exactly vector in the conventional sense. So that's the name. So if I say the entries of the matrix, those are these. So the entries of 1, 2, 3, 4 are 1, 2, 3, 4. Right? The entries are the actual items that are in the matrix.
So we read it from left to right?
Entries are elements.
So we read it from left to right?
No, you don't have to. Right? We're going to talk about that later on, about how we enumerate the entries. Right? 3. The sequence of entries in a horizontal line is called a row. 4. Rows are numbered top to bottom, beginning at 1. Columns are numbered left to right. Also beginning at 1. So for example, if I look at the matrix again, 1, 2, 3, we're getting a lot of mileage out of this one. Or 1, 2, 3, 4. Then if I look at this guy, I call this the first row of the matrix. This guy would be the second row of the matrix, right? So I start by, this is row 1, row 2, row 3, number them going down. This I would call the first column of the matrix. This I would call the second column of the matrix. So column 1, column 2, column 3, column 4 is to number of columns from left to right starting at 1. Sort of like quadrants where you start at the top and that's 1 and then you keep numbering. But we're not numbering things in a circular fashion because that gets confusing. So, 5. A matrix with n rows and n columns is called a, what's it called?
N by N matrix.
Which one?
N by N?
No, it's the m first.
N by N, yes.
Right? It's red, n by n matrix. This is called the dimension of the matrix.
Why?
Dimension is just size, so I'm telling you the size. If I say
So
it's
it's
a
like an
3
area?
by 2. No, it's just the dimensions
Okay, fine.
of the matrix. So for example, so what kind of matrix is this? What's the dimensions?
2 by 2?
2 by 2.
Yeah,
2 rows, 2 columns. This is a 2 by 2 matrix.
3 by 2? Yes, sir.
And this one
2
is a
by
what?
3.
2 by 3.
Yeah.
Count the number of rows,
Yeah.
you have 2 of them. Count the number of columns, you have 3 of them. You put the rows before the columns. This is called a 2 by 3 matrix. Still on definitions. A lot of definitions to write out because we're doing something different. You have to know the language of what we're talking about, right? So if I mention the dimension of a matrix, I want you to know what I'm talking about, so we're going to have to do this.
Matrix?
Let's say 6. The element in the ith row and the jth column is said to be in the ijth position. It is denoted using subscripts to lowercase letters. Example, Aij, right? That's how you call that represents the element in the ith row and the jth column, which that was actually on your exam, on the quiz. So for example, 1, 2, 3, 4, 5, 6, and I ask you, what is A of 2, 2? Right?
2, 2, 5.
Right. So this is the number that's in the second row and the second column. So this is the second row, this is the second column. That's the second row, second column. This is the guy, right? That's 5, right? What if I ask you about A, 2, 3?
6.
6. So I look in the second row, third column. And in the
What
second
if it
row,
exists?
look in the third column, that's going to be 6.
What if it doesn't
If I
exist?
say A1, 2, 2.
2.
What doesn't exist? Like you say A3, 2.
Yes, it doesn't exist.
Okay.
would
Will you
know
trick us
how-
like that?
Huh?
Will you trick us like that?
Yes?
Can you use double summation note? Actually.
No, it's not a double summation. The matrix, you can use this notation to represent the matrix. I don't know if that's what you're asking. So with this notation, we can call the matrix Aij, but you put brackets over it. Right? The matrices themselves are usually denoted by uppercase letters. Denoted by uppercase letters. So I can say A equals 1, 2, 3, 4. Right? So when I use uppercase letters, I'm talking about the matrix itself. If I'm talking about the elements in the matrix, I can use lowercase letters and give you the little subscript here that tells you particularly what element I'm talking about. Or in this case, I can just write A is equal to the matrix Aij, right? This is if I want to describe the matrix in terms of its elements. I can write something like this.
You can't describe its elements with the uppercase.
No, it's not conventional.
Question. Can we say A is equal to brackets and then some like A and then some semicolon B, C, etc.
Usually use that in a programming language, not when you're writing it down by hand.
I'm a little confused by that. Is it literally Aij, or is it like in this situation A22?
No, Aij, because it ranges, right?
Okay.
It consists of A11, A12,
Okay.
A21, A22, right? So your ij vary to cover the whole matrix, right? It will be understood what these guys are. Sometimes they'll actually tell you I goes from 1 up to like something, if they want to define the dimension, right? So they'll tell you that separately. But if they just leave it as I and j variables, it means it ranges over the whole matrix. Seven, if m equals n, we call the matrix a square matrix. Example. R squared matrices. Alright, so this is a 2 by 2, this is a 3 by 3, m is equal to n, we call it a square matrix. Non-example 1, 2, 3, 4, 6. Square matrix. Alright, because this is a 2 by 3 matrix. The m is not equal to the n. Okay. So you have to know what square matrices are, because there are things that only work with square matrices. For example, determinants. You can only take a determinant of a square matrix.
What if you try to do it on a non-square matrix? So that
You can't. It makes no mathematical sense. Because the idea is you also use determinants to define things like inverses. I mean, I tell you that a matrix is a rectangular array of numbers, but mathematicians really don't think of matrices that way. We think of them as like linear functions, right? Linear transformations. And so we think of them as functions from an m-dimensional vector space to an n-dimensional vector space. And so that's how we think of them. And then you use the determinant to define the inverse, which means you need to map onto one set and map back, so the dimensions have to line up, they have to be the same dimensions, or else your inverse function wouldn't exist. It doesn't make any sense to talk about the determinant in the first place. But yeah, that's...
So why do rectangular matrices exist?
Yeah.
Why do non-square matrices exist?
Those are other functions, right? So for example, this guy I can think of as a function from a 3-dimensional vector space to a 2-dimensional vector space. So for the idea is if I say, let's say I have a function, right? Just digress as linear transformations. Right, so I'm not going to finish all the definitions anyway, so we can digress a little bit. Right, so you think about a linear transformation, right? Now, a linear transformation is a function f with the following properties. Right, it's a generalized kind of function. It's linear, meaning that if you take f of x plus y, it's just the same as f of x plus f of y. And it's also, you can factor scalars out. So if you say f of k times x is the same as k times f of x. Right? For example, the derivative is a linear transformation. If you take the derivative of a sum, it's the same as the sum of the derivatives. If you take the derivative of a constant times a function, same as the constant times the derivative of a function. So your derivative you can think of as a linear transformation. Right? So that's an example of a linear transformation. You're sort of generalizing a function that has those two properties. Well, if you think about a matrix, let's say I'm thinking about a function from R2 to R2. I could say something like f takes each coordinate in R2, x, y, and it maps it to the coordinate that looks like ax plus by, comma cx plus dy. Right? So I can describe that function. Right? So I take each coordinate and for some constants a, b, c, d, I map this coordinate to that coordinate. Right? That's a function from R2 to R2. Right? If I wanted to, just because, I could actually write this as something like this. Right? This is sort of like writing that matrix, writing it as a matrix where it's a column. And since I know that the first column is the x, the second column is the y, I can, they're superfluous. I can sort of leave them out. So I can write it as a, b, c, d. Right? So when I write down this rectangular array of numbers, what I'm really thinking about is that particular function.
That's why it can be noted as vector.
So that's why it can be like a vector. And so if I have 3 coordinates here, right, mapping to 2 coordinates there, right, what's going to happen is I would have actually 3 columns here, right? So if I think of if it's going from, so f can be represented by a 2 by 2 matrix. And so you can think of matrices as these functions. And when you look at things like matrix multiplication, which is usually a mystery to most people, this is the interpretation that makes sense, right? So, you had a question?
Yeah, so that's the coefficient matrix?
Yes, this is called the coefficient matrix. And we'll talk more about that in chapter 2.
The above one is a 2 by 1 matrix, right? Above one, ax plus by, cx plus...
No, this is a comma.
No, below that.
I'm thinking of it as a
The
difference.
one below that, the one below that. That's 2 by 1, right? There are 2 ax plus by.
No, this is one formula. That's...
Yeah, so that's...
Yeah, this is a 2 by 1. That's what you're asking? Yeah.
So we can imagine the matrix multiplication.
Well, when you look at that, that's not where you see the matrix, because you have addition.
That's the matrix
When you
multiplication.
think of this part as the matrix, you think of it as a 2 by 2, which tells you you're going from a 2-dimensional space to a 2-dimensional space. Right? So you're going from ordered pairs to ordered pairs. Right? So if I wanted a function from, say, R3 to R2, right? So this would mean I am mapping x, y, z to just a coordinate where I have a function of x, y, z to another function of x, y, z. All right, so I'm mapping a 3 tuple to an ordered pair, right? Then this would be given by a 2 by 3 matrix.
So basically the mapping implies your domain, from what domain you're going, what range? Okay.
Right. So, for example, that's why determinants are only for square matrices, because a determinant helps you define an inverse, which means that your domain has to be the same size as your range so that you can reverse them. Right? And that's why you need square matrices to find a determinant. Right?
Okay,
And so it's not really defined in general.
Multiplication for matrices is kind of like
Right, so
vectors.
multiplication for matrices, it's actually sort of weird. I'm actually going to define that later.
So it's like dot product, cross
So if
product.
you look at something like multiplication, and you take this matrix A, B, C, D, times another matrix, E, F, G, H, do you know what the answer looks like?
Goes in by columns, right?
E plus BG is the
Right,
first.
you don't multiply corresponding components, which seems to be the obvious thing to do. It actually doesn't work, it doesn't make sense. The actual answer would be to take this row times that column, you have A, E plus BG, And then take this row times this column. You have AF plus BH. Then take the second row times this column, CE plus DG. Then take this time, right? So we have CF plus DH. We're going to talk more about this later on, so don't worry about it. Right? So
CE plus DG, how do you...
don't worry.
So
We're going to find addition and subtraction. That's matrix algebra, right? So we're going to find addition and subtraction, and that's going to be the obvious way. That's going to be how you think you would add them or subtract them. Then we're going to get to multiplication, and we're going to do something like this. You're going to be like, what the hell? What is that about? The real reason why it has to be defined this way is because of this interpretation. We're thinking of them as functions. And so matrix multiplication actually models a composition of functions, right? When you multiply two functions, you're thinking about it as composition, right? You're not thinking about it multiplication in the usual sense. So let's say, for example, I have a function a from R2 to R2, right? And it's given by A, B, C, D, right? So that is, it takes x, y, and it maps it to ax plus by, comma, cx plus dy, right? And I have another function that I call b, also from R2 to R2, that maps cx ex plus gh. Right? So I say it's given by the matrix E, F, G, H. Right? I can write that. So when I take A times B, how am I thinking about that? Right? I can't interpret it as real numbers, right? If you take one number times another number, you can think of it just repeated addition, right? You say 2 times 3, it's just 2 added to itself 3 times, or 3 added to itself 2 times. What does it mean to add a matrix to itself a matrix amount of times? It doesn't make any sense, right? Or you can think of multiplying two real numbers as finding the area of the rectangle, where the side lengths of the two numbers. It still doesn't make sense for a side length of a rectangle to have a matrix as its value, right? So how do you interpret multiplication? Well, you interpret it as composition. You think of it as A composed with B, right? Composition. In other words, you take one function and you plug it into the other, A, and you plug in B of x, y, right? So if you have A of B of x, y, what does B do to x and y? Well, it gives you this vector here, right? So this would just be A of this coordinate, Ex plus Fy, comma Gx plus Hy, right? But then, what does A do to any coordinate that you give it? If you think of this as the new x and this as the new y, what is A going to give you?
Multiply by A.
It's going to take A times this coordinate.
Oh, I see.
Plus B times the second coordinate, comma. Then it's going to take C times the first coordinate.
What does the composition do?
Plus CD times the third coordinate. And it makes that coordinate. But what is that? It's equal to the coordinate AE times x plus AF times y, comma, plus BG times x plus BH times y, comma. Right? Here I can start writing it as columns, right? The comma comes after that. And then in the second component, we're going to have what? CE times
Why is there a
x.
plus between your two nodes? your AFY and your BGX, they go to plus?
Yes, all this is in the first coordinate. Right? A times this plus B times that. That's all in the first coordinate.
He's just opening the parentheses.
Right? And I write that first coordinate on the top. And then I'm going to have CE plus CF.
Plus DGX plus DHY.
DGX plus
DHY.
DHY, right? Now if I group all the x's here, right, I'm going to have AE plus BG all times x plus AF plus BH all times y. And then I'm going to have CE plus DG all times x plus CF plus DH all times y. And if I do what I did before, just ignore the x's and y's because they're superfluous at this point. I know the first column is the x's. I know the second column is the y's. Just ignore them. Then I have AE plus BG. Was that BG?
Yeah.
Yeah.
DGX.
Yes.
And then I would have AF plus BH. I would have CE plus DG. And I would have CF plus DH. And how did I define matrix multiplication before? That's exactly how.
Is there a shortcut?
The shortcut is to know that you take the rows times the columns, the rows times the columns. I'm going to define that later on.
Okay.
But the point is, when I give you this definition, most people don't know where it comes from. It turns out it comes from this interpretation here. We're thinking about these guys as functions, and we're thinking of multiplication as composition of functions. And if you plug one function into the other, it turns out you end up with something that looks like this. So later on, next class we're going to do some more definitions, and we're going to talk about multiplication, how to add two matrices, how to subtract two matrices, how to multiply matrices. We're going to talk about determinants and diagonals and identities and all that stuff. Lots of fun stuff to come. And we'll end there for today.